Good morning to you all.
Good morning, ma'am.
Good morning, ma'am.
So today's session, we will start with continuous probability distribution. This is another part of probability distribution. Already we introduced discrete probability distribution. And we learned about how we can calculate the expected value, variance, and especially for two theoretical distributions, we learned about the binomial and Poisson. And from that also, we learned how we can calculate the probabilities, what are the probability distributions, how we can calculate the expected value and the standard deviation for the specific probability distribution, right? So actually, when we started our learning on probability distribution, first we introduced the random variable. The random variable we divided into two cases. One is a discrete random variable, and other one is the continuous random variable. For any probability distribution, we are constructing for discrete random variable, that is a discrete probability distribution. If a random variable is continuous, then we can say that the corresponding probability distribution is continuous probability distribution. So the learning outcomes, first learning outcomes, you will be able to understand the difference between the discrete and continuous probability distribution, right? That means you will be able to distinguish the discrete and the continuous probability distribution. And also, like binomial and Poisson, here also we introduce a theoretical probability distribution that is called the normal probability distribution. This is very important for the all statistical applications are depending on this normal probability distribution. So the basic understanding of this normal probability distribution is very essential, right? Then you will be able to distinguish between the normal and the standard normal distribution, and you will be able to calculate the probabilities using the normal distribution, and also you will be able to use normal distribution to solve some sort of business problems, right? So this is the recap of the previous chapters we learned, discrete random variables and their probability distribution. Now we are extending the concept to the continuous random variables and their probability distribution. So as a brief, what is the discrete probability distribution? So whatever probability distribution we are going to define, then in that probability distribution, the two specific things we have to say that one is the probability of the occurrence of each value of a discrete random variable, right? So the discrete probability distribution describes the probability of occurrence of each value of a discrete random variable. If there is how many values are there, according to that, for each and every value, we have to give the probability, right? And a discrete random variable is a random variable which has countable values, right? That means we are able to count it. With the discrete probability distribution, each possible value of the discrete random variable can be associated with a non-zero probability. And also we can present this discrete probability distribution in a tabular form or in a formula form, right? Because very first we learned how we can produce the probability distribution in a tabular form, in the graphical form, but in the later we learned the binomial and Poisson. For these two probability distributions, we used formula to tabulate to describe each and every probability of the random variables, right? Then now we are coming to the today's session, continuous random variable. So a random variable is continuous random variable if it can take any value in an interval, right? So actually for the continuous random variable, we cannot list these are the specific values, right? Always we have to specify the values of the random variable in an interval form. Within that interval, each and every value is possible. So there are infinite number of possible values for a continuous random variable, right? And also, usually for the continuous random variable, we are taking the values by measuring, right? But in the discrete random variable, we are taking the values by counting, right? So for examples, for the continuous random variable, the yearly income for a family, right? So we are measuring our income with the rupees and cents, right? The amount of oil imported into Sri Lanka in a particular month. So here we are measuring the oil in the liter or whatever big measurements we are using, but we are not counting, all right? We are measuring the oil. The change in the price of a store of IBM common stock in a month. Here also prices are measured by the dollar or rupees or whatever units we are using. That based on that unit, we can measure the prices. The time that elapses between the installation of a new component and its failure, right? How long it will alive, right? The particular new component. So the expired time, we are lifetime of the component, we are measuring using the clock, or days, or year, or months, right? So this is also months and with days and months with times. So here, these are the continuous random variables, right? Now there is a small exercise to get understanding. Consider the experiment of filling 12-ounce cans, right, with coffee, and let X be the amount of coffee in a randomly chosen can. Find the values of the random variable X. Anyone guess the answer for this one? Right, there is a can is there. The amount of that can is 12 ounce. Maximum, it will consist 12 ounce. So now we are taking a random variable and we define that random variable as a amount of coffee in a randomly chosen can. There are a lot of cans are there, and we are picking up one can and we want to identify how much of amount of coffee is there in the picked can. So how you can describe the values for X? Is it continuous random variable or discrete random variable?
Continuous.
Right, continuous random variable. Then how you can define the values for this variable, the possible values? How you can define it? So first you think about, if it are continuous, then we cannot list one by one, right? So we have to specify those values in an interval form. So if we want to specify the values in an interval form, we have to know the minimum value and we have to know the maximum value. Within that interval, each and every value is possible. So in this case, what value would be the minimum? If there is no filling, then what is the possible value?
0.
0. Maximum, how much we can fill?
12.
12. 12. So how you can specify the values for this random variable? The values are in between 0 to 12, including 0 and 12, right? So how we can specify now these values? For example, so now we know that X is a continuous random variable. According to the definition of this problem, continuous random variable. So if it is a continuous random variable, based on the concept of continuous random variable, it will take the values in a specific interval form. So if we want to specify the interval, we have to know the lowest and the maximum value. So here we know that the minimum value, if there is no any coffee in the cup, then that will be 0. So the minimum value 0 less than or equal to x less than or equal to 12. Maximum 12 ounce or minimum 0 ounce. In that, any value is possible. So the values of the random variable is given by this one. Or you can write x belongs to 0, 12. Because 0 also included and 12 also included, right? So these are the possibility of specifying the random variable. So in one way, you can write in such way, or you can use this notation also to specify the values of the random variable, right? Now another working scenario here we are looking at to get the understanding of a continuous random variable and how we can use this continuous random variable to calculate the probabilities related to some events, right? So here it's regarding the banking, particular bank's website, and we need to make sure about the home page downloads quickly, whether in the home page, how long it will take to download the home page of a particular bank. So if the main thing here, we know that if the home page is downloading quickly, then it will attract and retain customers, right? So if the downloading home page is taking more time, then what we will do, we close the website and we leave it, right? And we will not be attracted that one. So if we want to attract the customers and retain our customers, particularly in the online banking, then the downloading the home page should be very quick speed, right? But the downloading time will be affected by the design of the home page and the load of the bank web servers, right? These both things will affect. So from the past experience, it was found that the mean download time is 7 seconds and the standard deviation is 2 seconds. That means it's most of the times are ranging in between 5 to 9 seconds, right? Because mean time is 7 and the standard deviation is 2. So according to the concept of standard deviation, we can say that most of the downloading times are in between 7 minus 2, 5 seconds to 7 plus 2, 9 seconds. But when we are looking at these downloading times, it was also found that about 95% of the downloading times are between 3 and 11 seconds, right? And about 2/3 of the download times are, that is, I think 65% or something, are between 5 to 9 seconds, and about 95% of the download time. Suppose when you are taking the 100 download times, then 95 times download times are 3 to 11 seconds. Nearly 63% of the times are 5 to 9 seconds. So in other words, if we have such kind of pattern, then mostly when we are plotting those probabilities, we will get a bell-shaped curve with clustering around a mean of 7 seconds. Right? Most of the observations are very close to 7 seconds. So how we can use this information to answer the questions about the download times of the current home page. So for example, what is the proportion of the home page downloads are take more than 10 seconds, right? So what is the probability that in the downloading time is greater than 10 seconds? How we can calculate? How many seconds elapse before 10% of the downloading are completed? So here we are looking at the time. Here we are looking at the proportion. So if we want to provide answers to these questions, then we have to look at the distribution related to a bell-shaped curve, right? This is one of the most of the our business related variables or economic variables. We say that all have a approximately bell-shaped curve, right? And also most of the 63% of the observations are fall from the mean one standard deviation, and 95% of the observations are falling from mean by 2 standard deviations, right? This is the specific characteristic of a bell-shaped curve. So what is a continuous probability? Now we are coming for the continuous probability distribution, right? So a continuous probability distribution describes the probabilities of the possible value. Same concept, whatever probability distribution we are taking, it is a discrete or it is a continuous, always we have to say, we have to show the probabilities and the corresponding values of the random variable. So the same concept here also we are applying. A continuous distribution describes the probabilities of the possible values of a continuous random variable. So for the possible values, what are the corresponding probabilities? And already we know that a continuous random variable is a random variable with a set of possible values, usually known as the range, that is infinite and uncountable. So if our continuous random variable has a bell-shaped curve, this is called as a symmetrical bell-shaped, right? Symmetrical bell-shaped. So usually the probabilities of a continuous random variable is defined as the area under the curve of its probability distribution. And also statistically, the probability distribution for the continuous variable is named as a probability density curve, right? The probability curve. When we are representing the probability distribution in a graphical, usually this is called as a density curve, probability density curve, right? Now here, if we want to find the probability, this random variable is denoted by x. Those values are given in the horizontal axis, and the vertical axis indicate the probabilities. Vertical axis indicate the probabilities, right? So now, usually for a discrete probability distribution, right? Now here, don't confuse that one. Usually for the discrete probability distribution, how we are saying that if x is a discrete random variable, then here we are saying that p x equals x, right? But here we cannot specify probability of, if x is a continuous random variable, this cannot be, in such manner we cannot say that, because for a continuous random variable, here we are saying that all the values are, each and every value in this, including the endpoints, all are possible, right? Each and every value including. So suppose when we are taking for a point wise, if we are specifying for a continuous random variable, if x is equal to 2, it is very, very, very small. It's approximately equal to 0, because there are infinite number of values. Now we say that in this interval, now suppose for example, there are 10 points and each and every point has a equal chance. Then 1 over 10. That is 0.1. Then say that there are 100 points. 1 over 100. Then 0.01. Suppose there are 10,000 or 1 lakh points or 1 million points. Then it is 0.00001 or 01. Now you look at when the number of points are increasing, the probabilities are decreasing and very close to 0. So in the continuous random variable, there are infinite number of points in that interval. So when we are specifying a particular value for this variable, continuous random variable, this will be very, very, very extremely small value. So approximately this is equal to 0. So if we are asking to calculate the probability for a continuous random variable with a specific value, then without any doubt you can say that it is approximately 0. Right? So usually we are calculating because total probability is 1. Right? Within that we have to assign the probabilities for each and every point. So it will be very, very, very small. So usually for the continuous random variable, we are calculating the probability in an interval form, right? So for this case, actually what is the probability for this one? How we can specify? This area will be the probability. For which values? Probability of the minimum value 160. Your random variable x less than or equal to 170. Right? That is here, the area is here calculated as (0.135905). This is the probability. Even when you look at even in 160 to 170, there are infinite number of points. For that also, there are 0.139505. Right? This is same as actually probability of even not equal sign also not necessary. Less than x less than 170. Right? Now, in both without equal sign or with equal sign, then both are same probability you will get, because when we are taking a specific value, the probability is actually 0. Right? So usually, how we are calculating the probability for the continuous random variable for the particular interval, what is the area it's included, that area will be the probability. Right? So, but in this area, usually in the first semester, you learned that the integration is used to calculate the area under the probability, right? Integration can be used to calculate the area under the probability. But here we will not use integration. We are going to use the statistical tables to calculate the probabilities for a continuous probability distribution, right? Similarly, for the continuous probability distribution, also the total probability is 1. So that means this is the total area under this curve. This is your probability curve. So this is the total area under the curve. Right? So the total area is 1. And also for a symmetrical bell-shaped symmetrical curve, this area, half of the area is equal to other half part, that is 50%, 50%. So the probability is here 0.5, here 0.5. Then the total probability is 1. If it is a bell-shaped curve and symmetrical about the straight line that passes through the peaked point, then it will be divided this curve equally 2 parts. So here the area is 0.5, here the area is 0.5. Then how we can distinguish the probability distribution and the continuous probability distribution, right? How you can differentiate the two distribution, discrete and the continuous. The probability that a continuous random variable will assume a particular value is 0, right? For a continuous probability distribution, if we are taking for a continuous random variable and it will assume a particular value, that is 0, right? Already we learned in the previous slides, and only we can calculate the values, ranges of for a ranges of values. We can calculate the non-zero probability for a ranges of values. This is very important point, right? If for a specific value, this is 0, only we can calculate a non-probability for a range of values for the random variable, right? So because of this, continuous probability distribution cannot be expressed in a tabular form. But a discrete probability distribution, we can express in a tabular form, but for a continuous probability distribution, we cannot express in a tabular form. Am I right? Because why we cannot express in a tabular form? There are infinite number of values, so we can't list each and every value. Because of that, we cannot express in a tabular form. So how we can express our probability distribution for a continuous random variable? In an equation form, that means a formula or a graph, right? In the previous slide, we used the graph. Is used to describe the continuous probability distribution, right? Usually, if we are using the formula, then that formula will not be tell as a distribution. For a continuous variable, the formula is generally called as probability density function. These kind of informations are very important for your MCQ exams, right? The wording, terminologies, what are the things we are using, that is very important for the MCQ questions, right? Now, we are coming for the specific theoretical distribution that is called a normal distribution. In the continuous probability distribution, like in the discrete, we learn two theoretical distribution. right? The normal distribution is the most common continuous probability distribution used in the statistics, right? For even for inference decision-making process, mostly for the statistical inference, we are using the normal distribution. So why the normal distribution is important? Because there are a lot of reasons. One, most of our variables in related to business have a distribution that closely or approximately follows the normal distribution. For example, many economic and business measures such as sales, investments, consumptions, cost, and the revenues can be represented by the continuous random variables and resemble the normal distribution, right? The normal distribution can be used to approximate various discrete probability distribution, right? The normal distribution can be used to approximate even the binomial or the Poisson. These both distributions can be approximated by the normal distribution under the certain conditions. And this normal distribution provides the basis for the classical statistical inference. So because of these points, this normal distribution is very important in the statistics, right? Then properties of a normal distribution, right? Or normal distribution always bell-shaped and symmetrical. Right? It is like when we are plotting the density function for the normal, you will get the curve in such manner, right? So it is a symmetrical about the mean value. Here, this point is if this is a random variable x, and this is the probabilities. Usually, for the discrete, only we are marking the probability px. But for the continuous f of x, the probability density function is defined by using the notation f of x. And this value will be the mean value. For a normal distribution, this curve is symmetrical about the axis that passes through the mean, mode, and the median, right? So, for the normal distribution, in the mean, median, and mode, all are equal, right? All are placed here. This is the mean value. This will be the median. This will be the mode. Mode is the highest frequency. This point is the highest frequency. So that is the corresponding x value is this one. So these three measures of central tendency 3, mean, median, mode, are equal for the normal distribution. Third one, the location is determined by the mean. That is the central value is determined by the mean. This is the location, right? And is denoted by mu, right? And the spread or variations is determined by the standard deviation. Variation is determined by the standard deviation. The length is depending on the variation. The length of the horizontal curve shows the variations among the data or variations among the data of a normal distribution that is denoted by sigma. But when we are taking the range for the normal distribution, it has an infinite range, right? Now we are looking at these endpoints. These are the tails of the distribution. In the tails always did not cut the x-axis. That means with the horizontal axis, the curve will not be intersected, right? It is approximates. It will go infinitely, but never touch the x-axis, right? It's never touched the horizontal axis, but it goes up to infinite values. So always it has an infinite range. So when we are taking for example, for a binomial distribution, how we are defining the value, by how we are defining the values for x. If x is a binomial random variable, then the possible values for x we are writing as a x for a binomial distribution. If it has n trials, then the possible values are 0, 1, 2, 3 up to n. Right? But if it's a Poisson random variable, then how we are denoting the value? X is equal to 0, 1, 2, 3, 4, but we don't know the maximum value. But for the normal distribution, how we are denoting the random variable values, it has an infinite range. So, minus infinity, less than or equal to x, less than or equal to infinity. Right? So, there are infinite number of values. Based on this point, we say that this the curve does not meet the horizontal axis, but it approximates, it approaches the x-axis, but not cut the x-axis, right? So the normal curve approaches, but never touches the x-axis. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So, because here it will take minus infinity to plus infinity values. So, we don't know the, for the normal distribution, we don't know the minimum value and we don't know the maximum value, right? Then the total area under the normal curve is equal to 1. So these are the properties of a normal distribution. This is the mean, median, mode will be located here. Right. Now we are looking at the effect of, so in the normal distribution also, these two parameters, mu and sigma, expected value, mean, and the standard deviation are the parameters. If we know these two parameters, then we can calculate the normal probabilities. For the even for binomial also, what are the parameters? Number of trials, n, and the probability of success. If we know these two parameters, then we can calculate the binomial probabilities, and also we can describe the binomial probability distribution. But for the Poisson distribution, we have to know the average value of the particular event in a certain area. The expect mean value should be known. That is denoted by lambda. Right? Similarly, for the normal distribution, the two parameters are mean and the standard deviation. Mean is denoted by mu and the standard deviation is denoted by sigma. If these two are the parameters, and if we know these two parameters, then we can specify the normal distribution function, and also we can calculate the probabilities. Right, now we will look at one by one parameter. First we are looking at the mu, right? Now you look at, in this case, mu is equal to minus 4. In this case, mu is equal to 0. In this case, mu is equal to 3. So, when we are changing the mean values, the distributions will move from left to left or right, right? Now, if it is a 0, because these are values for the mean values also in the horizontal axis. So, now it is a 0 here. Now, when mean value is 3, the curve is moved towards right. right? The curve is, now from this is the curve when mu is equal to 0. Now this is the curve when mu is equal to 3. When the mean value is negative value, it's moved towards left. When it's taking the negative values, it moves, if it's the location is towards left. So changing mu shift the distribution left or right. But changing the sigma increases or decreases the spread. Now we are looking at here sigma is equal to 0.5. Now you look at the spread, and in this case sigma is equal to 1.5. So the spread is larger than the first curve. In this case sigma is equal to 1. So it is smaller than the purple colored curve. So the spread is the length in between the two tails. The length in between the two tails. Right? So when the spread is small, standard deviation is small, the length in between the two tails will be also small. So when the sigma getting smaller, the length between two tails also will get smaller. Right? So changing sigma increases or decreases the spread. So when it's the length is decreases, now you look at the peaked also. It becomes more peaked. The length is getting smaller. The peak also getting more, very high peak you will get. When the sigma is increases, the peak will get flatter. Right? The peak will get flatter. Right? So this is more peaked. But when we are comparing this one, the curve with the larger standard deviation, more flatter comparing to this curve, right? So by changing the mu, it will displace the curve from left or right. But when we are changing the sigma, the length between the two tails and the curve peak will change, right? So by varying the parameters mu and sigma, we obtain different normal distribution, right? That is that the curve is always bell-shaped, symmetrical, but the peak, flatter, and the locations will be changed, right? So now we are looking at this example. Right, now looking at these curves, can you say which normal curve has the greater mean? There is a curve, two normal curves, A and B, both are symmetrical and symmetrical about mean values, right? So according to the appearance, which normal curve has the greater mean, A or B? Anyone? Unmute your mic and say, which normal curve has the greater mean value? What is the mean value for normal curve B? Looking at the graph and say, what is the mean value? 12. Right. For B, 12. For A?
15.
15. So now, which is the greater mean? Which curve has the greater
A.
Curve? A, right? So, because how we can identifying the mean value? We have to draw the symmetrical axis that divide the curve into two equal parts. So that line is this one, that it passes through 12. So 12 is the mean for curve B. So similarly, this is the center line. It divides the A curve by two equal parts. So this is the mean value B. So 15 is the larger mean value. So the normal curve A has the greater mean. Right. Which normal curve has the greater standard deviation? Which normal curve has the greater standard deviation? How we can identify the standard deviation? We have to look at the length between two tails, right? To identify the standard deviation, whether it's smaller or greater, you have to look at the length of the tails, right? Length of the tails of a curve. Length between two tails of a curve. So when we are taking B, this is the length. It ranges from nearly 5 to 21. 21, nearly 16 points or 16 units. But if you are looking at A, 12 to 18, that is 6. So B has a larger length comparing to A. So the greater standard deviation, the curve, normal curve B has greater standard deviation comparing to A. So when the lengths are decreasing, the flatter will become peak. Here, the curve B has more flatter comparing to A. So, right. For the normal distribution probability, the probability is area under the curve. This is already we learned that the probability we can calculate the probability under the area. So the probability that the random variable exists. So here, how we can define this one, probability C less than or equal to X less than or equal to D is this shaded area. The probability of X between Z to D is area of shaded. So this is same as actually probability of C less than or equal to X less than or equal to D. That is also for both the same. This is also, you can write this also, probability of C less than or equal to X less than or equal to D. Both the same area, right? Then another special kind of normal distribution called the standard normal distribution. Right? The standard normal distribution is a normal distribution with mu equals 0 and sigma equals 1. The standard normal distribution is a normal distribution with mu equals 0 and sigma is equal to 1. Right? That is a special kind. So a random variable with a standard normal distribution denoted by Z. Normally, the standard normal distributions we are denoting by X, but a standard normal random variable is denoted by Z. Right? And here it has a mean mu 0 and the sigma 1. This is a specific distribution, right? Zero, 1, 2, 3, 0, minus 1, minus 2, 3. Standard normal random variable, right? Any normal distribution with any mean and standard deviation combination can be transformed into the standardized normal distribution, right? Any normal distribution with any mean and the standard deviation, we can transform. How we can transform? We have to use this formula. So when this is particular normal value, random variable value, minus mu divided by sigma. This is if X has a normal distribution with mean, mu and sigma, then the particular X value should be transformed into the standard normal value by applying this formula. Right? So in this case, this variable has mean 0 and the standard deviation 1. Now graphically how we are transforming. Now this is a X random variable. It has mean mu and the standard deviation sigma. Then for each and every X value is transformed using this formula, right? Then when we are plotting these corresponding Z values, then we will get a curve in such manner. And here the mean is 0 and the sigma is equal to 1. Right? This is very important. By using this standard normal, we are going to calculate our probabilities. Right? Then specifically for a standard normal or any normal curve, these are the some distribution pattern we are having, right? So in the first case, approximately 68.26% of the measurements will have a score between -1 to 10. Suppose we are taking 100 observations, which are the standardized values, right? 100 observations, which are the standardized values. Then, suppose we say that 100 students marks we are taking, right? And for each and every student marks, we are converting to the Z score. Then, around 68% of the students, Z score will be -1 to, in between -1 to 1. Right. Then if we take 100 students' marks, right, and if we are converting all the students' marks in the Z-score using the previous formula, then 95%, around 95% of the students' Z-scores will be -2 to +2. Right? Similarly, almost all the students' marks will have a Z-score between -3 to +3. This is the distribution pattern. If your marks has a normal distribution, right? If your marks has a normal distribution, then this pattern will be followed. So when we are representing these points in a curve, this is Z. This is mean value 0. And our standard deviation is -1, +1. So +1, -1. Then Z scores. These are the Z scores. So this area is 68.26%. Okay? For this one, zero, 2, -2. Then this, the probability of having the students Z-score -2 between 2 to, it is 95.44%. Right? For this one, and -3. This is 99.74%, right? So now we are writing in the probability terms, probability of -1 less than or equal to Z less than or equal to 1 is 68.26%. This is probability of -2 less than or equal to Z less than or equal to Z. 2 is equal to 95.44%. This is probability of -3 less than or equal to Z less than or equal to 3 is equal to 99.74%. Right? So this is the interpretation of the Z-scores for the normal shape distribution of data, right? So if it's a normal distribution, the data will be distributed in such manner. Now we are ready to finding a probability corresponding to a normal random variable. So if the random variable has a normal distribution, then we will look at how we can calculate the probabilities. The first step, you have to sketch the normal distribution, rough normal distribution, indicate the mean and the shade the area corresponding to the probability you want. Second one, you have to convert the boundaries of the shaded area from X values to standard normal value. Usually, we are calculating the normal probabilities for the range of values, right? There will be a boundaries. One may be for a certain boundary, it has a lower limit and upper limit. For some of the boundary, it has only the lower limit. For some of the boundary, it has only the upper limit. So according to the boundary values, all the boundary values should be converted into the standard normal variable using this formula. Z equals X minus mu over sigma. Then, so that means show the Z values under corresponding X values. Then we have to use the standard normal table to find the areas corresponding to the Z values. So when we are finding the corresponding values using the standard normal, sometimes we have to use the symmetrical total probability point, symmetrical point. These are the things we have to use to calculate the appropriate probabilities, right? Now you all have the standard normal variable that, standard normal table that was uploaded in the LMS. So you also take that table. Right? This is the table we are going to use, right? Area under standard normal curve. When we are taking this diagram, right? So this is the shaded area. These are the probabilities listed in the table, right? Like the probability in between 0 to Z. These are the probabilities listed in the table, right? So suppose, for example, this probability, Z value, when Z value is 0, this probability is 0. This is Z value is 0.01. Right? Now suppose we want to get the probability for Z value corresponding to, if Z is equal to 1, right? If Z is equal to 1, then this is the term, 0.3413. If the Z is 1, then the probability between 0 less than Z less than 1 equals 0.3413. If the probability, we want to get the probability Z equals, probability in between 0 to 1.25. Probability in between 0 to 1.25. So it is 1.2. Then we know 5. 0.5. So 1.25 is 0.3944. 0.3944. Right? The probability in between 0 to 1.25, 0.3944. Similarly, by using this table, we can calculate the probabilities, right? Okay. Right, here also 0 to 1.5, 0.4332. Right. Now here we are going to use the standard normal table to calculate the probabilities. So here there are 4 examples given to here. Given a standardized normal distribution, what is the probability? Now, all these are in the standard normal, right? So there is no need to transform it. We have a standard normal. Then if the Z is less than 1.17, Z is greater than 1.84, Z is between 1.57 and 1.84, and Z is less than 1.57 or greater than 1.84. So we will go one by one. So first, Z is less than 1.7. So first we have to put this in the graphical form, right? We have to put this one in the graphical form. So we know that the curve is standard normal distribution. So bell-shaped curve, right? So we are mark this one. Don't need to put this this curve, right?
Yeah.
This is 0 and this is Z, right? Now we want probability that is Z less than 1.7. So in the notation form, if that is our normal probability, Z is less than 1.57. this probability we have to calculate, right? So now here we have to mark the point 1.57. Now say that this is 1.57. Right? So from this, this whole area we have, because z less than 1.7. So this is the area covered by less than 1.7. So now this area we know that 0.5. This area, because symmetrically it will be divided by half. This is 0.5. So only we need this area. So this one equal, we can write this as a probability of z less than 1.57 equals 0.5 plus, what is the probability of this area? We can write as a probability of 0 less than z less than 1.57. Right? So that is 0.5 plus this area we have to use the table to calculate, right? Now how we can find the, you take the table. Oh. So wait. And take the table. We need point 0 to 1.57. So 0 to 1.57, 1.5, then we need 7. This one, right? 0.4418. One point 1.57. 0.4418, right? So this is equal to 0.4418. That is equal to 0.9418. That is 94.18%. Right? This is the probability. So probability that z less than 1.57 is 94.18%. Similarly, given a standardized normal distribution, what is the probability that z is greater than 1.84? So now we have to get the probability of z greater than 1.84, right? So according to this one, the diagram will be z 0, it is 1.84. So we need this probability. But in your table, you can get only this kind of probability in between 0 to this value. So how we can calculate? This one is equal to, we know that this total probability is 0.5. So 0.5 minus probability of 0 less than z less than 1.84. Right? If we deduct this probability from 0.5, then you can get the value for this value. Right? So from the table, you check with the table, 0 to 1.84, what is the probability? Anyone, can you say from the table?
0.4671.
Right, 0.4671. Right, that is equal to 0.0329. 0.0329. That is 3.29%. Right? Then next part. Given a standardized normal distribution, what is the probability that Z is between 1.57 and 1.84? So here we need the probability of that, 1.57 less than Z less than 1.84. Right? That is equal to, so first we draw the diagram, then easily we can identify the areas. So symmetrical, Z 1.57. It is 0, it is 1.57, it is 1.84. This area we need. So how we can calculate this probability? This is equal to probability of 0. Now we can get this probability from the table, right? Actually, this is equal to 1.84. This probability minus 1.57, right? So probability of 0 less than Z less than 1.84 minus probability of 0 less than Z less than 1.57. Right? Because why here we are converting in such manner? Because when we are using the table, only these probabilities we can get from the table, right? So because of that, we are writing this probability in such manner to use the table. Right. Then the probability between 0 to 1.84 is 0.4671 minus it is 0.4418. That is equal to 0.0253, that is 2.53%, right? Then the next part, given a standardized normal, what is the probability that Z is less than 1.57 or greater than 1.85? P Z less than 1.57 or Z greater than 1.84. Now, if we we are taking these two things, when we are taking the graph, that less than 1.5. This is that less than 1.7. Or we need z greater than 1.8. 1.8. So if we take these two, if we look at these two graphs, these two are disjoint events, mutually exclusive events. So here this probability we can write as a probability of z less than 1.57 plus probability of z greater than 1.84, because all these two are disjoint events, so we can put the plus sign, mutually exclusive, right? Then probability of z less than 1.7 is equal to 0.5 plus this probability, 0.5 plus probability of 0 less than z less than 1.5 plus this probability is this one greater than, right? So 0.5 minus probability of 0 less than z less than 1.8. Now 0.5, 0.51 plus this probability 0.4418 from the table minus this probability from the table 0.4671, right? So that is equal to 0.9747, that is 97.47%, right? Then now if probability is known, then how we can calculate the corresponding z values, right? If the probability is known, then how we can calculate the corresponding z values. So now here we look at this one. We want to get the z value. This value we have to find out. The corresponding probability is given by A, right? Probability of z greater than za. So now here we are marking probability of z greater than za. This is za. This area is probability of z greater than za. That is A. Right. So if this is the area, then this value we have to calculate, right? So if this area is known, then we can calculate this area. This is a 0.5 minus this area. Then in the table, we have to search where this area is located, right? Where this area is located. Based on this location of this area, then we can identify the corresponding Z value, right? Right. So now we take a simple example. Right. There are two questions are there. What is the value of Z if only 2.5% of all possible Z values are larger? Or between what two values this will be, right? Now we will go one by one. First we will take this one. So according to this one, first you have to draw the diagram. So what is the value of Z if only 2.5% of all possible Z values are larger? Right? So take a rough diagram. Only 2.5% of all possible Z value are larger, right? So according to that one, 2.5% of all possible value larger. This is the larger Z values. Only 2.5% should be larger Z values. So now this one we have to get. Right? So this is 0.025. 2.5%. When you are dividing by 100, then 0.025. So this area you can calculate from 0.5 minus 0.025, that is equal to 0.475. 0.475. Now, according to this case, now we have probability of Z greater than or equal to ZA is 0.05. From this, we can write probability of this is 0. 0 less than or equal to Z less than or equal to ZA equals 0.475. Now we need this value. We have to find what is this value. So this is the area. This probability is for 0.475. Now, based on the table, now we have to find out where this 0.475 is located in the table, right? So now we take a table. Now we will search 0.475. So 0.44447 here. This is 0.475. Right? This is 0.475. So here it is 1.9. Right? It is 1.9. And where the intersecting row? 1.96. It is 1.9 and here 0.06. When this column and this row is intersected at this point is 0.475. So our ZA is 1.96. So from the table, ZA is equal to 1.96. So for 1.96, if that only 2.5% of all the possible values are larger when z is equal to 1.96, right? So that means probability of z greater than or equal to 1.96 is equal to 0.05. Right? Similarly, for the next question, between what two values of z will the middle 60, this one with the middle, between what two values of z will middle 68.26% of all the possible z values be contained. So here first we will mark that 0. Middle 68.26 means when we are dividing 68.26, so somewhere here we will get this is middle 68.26%, right? So by symmetrical, if this is ZA, by symmetrically this is minus ZA, right? By symmetrically this is minus ZA, right? So when we are dividing this one, 34.13, that is 0.3413. So that means this area, probability of 0 less than z less than ZA is equal to 0.3413. Now we have to get the table because now we find out this area is 0.3413. So based on the table, now we can get the idea of the ZA value. Uh, 0.3413, right? Where 0.34. 0.34 this is 0.3413. What is the Z value? 1.00, that is 1. Right? So now if we get this one, so from this, ZA is equal to 1. So now from that means probability of minus 1 less than or equal to Z less than or equal to 1 is equal to 0.6826. Right? So all possible values, 68.26% of all possible values fall in between minus 1 to plus 1, right? 68 point, so how you can write the answer? 68.26% of all possible Z values will be contained between Z equals minus 1 and Z equals 1. Now this is the exercise. You take it as a homework and you practice it. And this is also the next class we will start with this computing normal probabilities. If a random variable, normal random variable has a mean and the standard. Now, so far we calculated the probabilities for the standard normal, right? So for the next class, we will calculate the probability for the normal distribution, right? So, any doubts? If you want, you can ask any doubts. And one more thing, here already for each and every chapter, the reading material also uploaded, right? So your exam questions, we will get from the reading materials, right? In such format, the exam questions will be get. Next week, you will have the exam from chapter 1 to 3, right? Already in the previous mid-semester vacation, I told that. So for the next week, you will have the exam. One of the day in the next week, you will have the exam. From chapter 1, 2, 3. So you practice what are the things in my slides and all the exercises we left as exercises, and the materials uploaded, reading materials uploaded in the LMS. You have to read carefully and study based on that two materials. On one, my PDF PPT, and other one is the reading materials, right? From that, the questions will be picked to evaluate you. Right? So next week, one of the day, you will have the exam. So be ready. If Sunday is possible, I will inform the class rep to have the exam. Sorry, not exam, class, Sunday morning. Otherwise, I will inform when the next class will be, right? The class, I will inform through the rep, and then the rep will inform the class time.